So we when we were working with conic sections in the first part of the chapter, and in our project, you've probably noticed that in rectangular coordinates, conics are nice if the center is at 0, 0. So our h and our k, and for a parabola, that'd be our vertex. But if our h and our k are 0, then our equations are much easier to work with. We don't have that x minus h squared, the y minus k squared. The equations are a lot easier to work with. Well, in polar coordinates, our conics are nice if a focus is at 0, at the pole, at the origin. I'm going to say at the pole. So if we put our focus at the pole and working in polar coordinates, our conic sections, the equations, turn out very nice. They're easy to work with, much like in rectangular coordinates, our equations are easy to work with if our center is at 0, 0. The other thing this is going to let us do, and one reason why this is important and why we're even talking about it, is if we put the focus of our conic sections at the pole, then we can describe all of the conic sections not as several different things, but as one thing. And we really basically have one equation. So in math, it's always nice when we can think of these separate things, we can bring them together, and really they're just different aspects of one thing. So that's part of what we're doing today. So we're going to do what we've done in the past with our conic sections. I'll write the locus definition of our conic sections, but now we're just going to have to write one definition because we can describe all the conic sections as one thing, and then we'll write our equations and talk about how we work with our equations. And the equations are going to be somewhat familiar because when we talked about polar equations, we worked with these equations. So let's start with our definition. So we're starting with a focus at the pole. So one focus is at the pole. So we're going to say the locus of points. And reminder, locus just means a set, a collection. The locus of points, so that the distance from a fixed point and that fixed point is the focus, is in constant ratio to the distance from a fixed line. The directrix. So the collection of all these points where the distance from the focus is in constant ratio to the distance from the directrix is a conic section. So there's our definition. The ratio is the eccentricity. So all that's changing here, the only thing that makes the conic sections different are that different conic sections have different eccentricities. So this is nice because we can describe all the conic sections as one thing. And all the conic sections now have a focus and a directrix. If E is less than 1, what kind of conic section do we have? So E is between 0 and 1. Do we remember? That's an ellipse. If E equals 1, we have a parabola. And if E is greater than 1, we have a hyperbola. So we have this constant ratio, the eccentricity, the distance from the focus to the directrix. If the eccentricity, that ratio is less than 1, our conic section is an ellipse. If the eccentricity equals 1, it's a parabola. If eccentricity is greater than 1, it's a hyperbola. And I'm just going to draw, just make a little sketch here. An ellipse. We have one focus at the pole, so it's going to be elongated on one side or the other. And the directrix is going to be closest to the vertex that's closest to the pole. And what we're saying is if we make the distance from this point to the focus and the point to the directrix, turn that into a ratio, the ratio is always less than 1. For a parabola, we already know that, I'm going to do it this way. There's our parabola. The focus is here, and the directrix is there. And the vertex is halfway between the focus and the directrix. For a hyperbola, I'll draw a hyperbola here. One focus is at the origin. We'll have another focus over here. The directrix is going to be closest to the vertex that's closest to the pole. Let me make that more vertical. So that's where our directrices would be for our different conic sections. And maybe I should need to redraw this one because in polar coordinates, I was not being careful, our focus is always at the pole. So all of our conic sections have directrices. All of our conic sections have foci that we already know. And we have this ratio that's important, the eccentricity. So this is a nice thing. Well, let's write, like we did before, now let's write our equations for conic sections. It's really, it's two equations, but it's really one equation. So the equation of conics. Our conic sections in polar coordinates, if our focus is at the pole, are going to look like this. EP over 1 plus or minus E cosine theta. Or R equals EP over 1 plus or minus E sine theta. And for our equations in polar coordinates, P, absolute value of P, is the distance from the focus to the directrix. So it's a little different than when we talked about parabolas in rectangular coordinates. In rectangular coordinates, P is the distance from the vertex to the focus, or the vertex to the directrix. In polar coordinates, P is the distance from the directrix to the focus. Well, let me back up just a second. The only reason we had to write two different equations is, well, let's think about this. What kind of symmetry does this have? This has polar axis symmetry. It's just a function of cosine theta. So this gives us polar axis symmetry. So when we see a cosine theta, we have polar axis symmetry. That tells us that our axis is horizontal. So any equation for a conic section in polar coordinates with a horizontal axis is going to have a cosine theta. And this, because it's just a function of sine theta, what kind of symmetry? Pi over 2. Axis symmetry. So it's going to be symmetrical about the vertical axis. So this is going to tell us that our axis is vertical. So that's the only reason we have to write the sine theta and the cosine theta. That's the difference between the vertical axis and the horizontal axis. We don't have to remember which one is positive, where the A is underneath, any of that. Just remember that cosine theta, polar axis symmetry, sine theta, pi over 2 axis symmetry. So all of that information gets condensed down into just one equation. We don't have as much to worry about. So let's look at an example. Questions so far? All right. Let's find we're going to do the same kinds of problems we did in section 9.1 through 9.3. Find the center, the vertices, and foci of the ellipse given by r equals 15 over 3 minus 2 cosine theta. And we'll talk in a little bit about, if we saw this equation, how to tell that it's an ellipse. Well, before we start doing anything, it says find the foci. We know, because we're in polar coordinates, one focus is at the pole. That's always the case in polar coordinates. One focus at 0, 0. What kind of symmetry does this have? Polar axis symmetry. And that means it's going to have a horizontal axis. So I'm going to draw a little picture over here. That means that our I want to say hyperbola and then I want to say parabola. Our ellipse either looks like this. There's our one focus. It looks like this. It's elongated this way. Or it's going to look like this. It's going to be elongated the other way. So part of what we're going to do is decide that. So we know it's going to look like this, and our center and our other focus is all going to be over here on the positive polar axis, our other vertex, and we'll have one vertex over here. Or this stuff's going to be shifted and it's going to be over here on the negative polar axis, over this direction. Well, let's figure it out. What does theta equal here? at this vertex or at this vertex? We get one vertex. When theta equals 0. So this vertex, that vertex is going to come when theta equals 0. Well, let's find what it is. R equals 15 over 3 minus 2 cosine of 0. What's the cosine of 0? Yes? 1. So this is 3 minus 2. So R equals 15. So we get one vertex at R theta is 15, 0. So this coordinate or this coordinate could be 15, 0. What is theta at this vertex? Zero, pi over 2, pi. So we get one vertex when theta equals pi. Well, let's plug that in and figure out what it is. R equals 15 over 3 minus 2 cosine pi. Cosine of pi is -1. So this is 3 plus 2, 5. R equals 3. So we get a vertex at 3 comma pi. So it's saying this distance is 15 and this distance is 3. So we know it has to be this one, because this distance is 15, this distance is 3. All right, we have the vertices. So I'm going to label this. This is in polar coordinates 15, 0, and this is 3 pi, the other vertex. We can think of this in rectangular coordinates as -3, 0. Where's the center? Halfway between the vertices. So our center is halfway between 15, 0 and -3, 0. So where is that? 6, 0. So there's our center here. And our other focus. Well, if this point is 6, 0, I'm going to erase this. If that point is 6, 0, what is C? From the center to the focus? 6. C equals 6. So I need to go 6 units from the center, 6, 0. So where's our other focus? 12, 0. So our focus is at 12, 0. So our other focus would be here. And there's all of our information. Isn't that nice? We don't have to remember a squared equals b squared plus c squared, or c squared equals a squared plus b squared. You don't have to remember any of that. We can get it all from the information we have. We don't have to remember which one is a and which one is b, depending on where it is in the equation. A is just the distance from the center to the vertex. C is the distance from the center to the focus. We could find B if we wanted to, and find the co-vertices. Really, we're interested in the stuff that's happening on the major axis. All right, questions there? We can shortcut our work even further by looking at the equation. That's what we're going to talk about next. We can figure out immediately if we have this situation or that situation. We can figure out which way our conic section is going to be situated. So let's talk about that. So we want to talk about the location of the directrix. So the first ones I want to talk about are horizontal directrix. All right, so let's before we write anything else down, if our directrix is horizontal, our major axis is going to be, if our directrix is horizontal, our major axis is vertical. The major axis is perpendicular to the directrix. So if we have a horizontal directrix, we have a vertical axis. Well, if we have a vertical axis, what is going to be in our equation for our conic? Sine or cosine? Sine. So we're going to have R equals EP over 1 plus E sine theta. Our horizontal directrix is above the pole. And if we have R equals EP over 1 minus E sine theta, our directrix is below the pole. So that's what the plus and minus tells us. Is the directrix above the pole or below the pole? If we have a vertical directrix, well, if our directrix is vertical, then our axis is going to be horizontal. And that's going to be our cosine equations. And we get R equals EP over 1 plus E cosine theta. And since our directrix is vertical and this sign is positive, where are you going to guess we're going to say the directrix is? To the right of the pole. And if we have R equals EP over 1 minus E cosine theta, our vertical directrix is left of the pole. So the plus and minus tells us above or below for horizontal directrices, right or left for vertical directrices. So really this, when we see our equation, we know basically everything about the conic section. It's almost like you could look at this equation and see the graph in your head. You don't even have to graph it. You just can see it. It's like Luke in Star Wars when he was fighting the little laser thing with his lightsaber and he put the mask on. You don't have to see it with your eyes. Use the Force. All right, let's look at another example. We want to find a polar equation. Find a polar equation of the hyperbola with vertices 1, 3 pi over 2, and 9, 3 pi over 2. And remember, in this section, when we're talking about polar coordinates, all of our coordinates are going to be in r theta, in polar form. Well, let's draw a little picture, just like we did in rectangular coordinates. But I'll draw my graph on rectangular coordinates. Well, here is 0, pi over 2, pi, 3 pi over 2. So here's 1, 3 pi over 2. And here's 9, 3 pi over 2. We know one focus is at 0, 0, always in polar coordinates. So our hyperbola is going to look like this. There's a rough sketch of our hyperbola. All right. Well, we have, what kind of symmetry do we have here? Polar axis? Do we have pi over 2 symmetry? Do we have pi over 2 symmetry, so our equation is going to have sine or cosine? Sine. It's got to have sine in it to have pi over 2 symmetry. The directrix is horizontal. Is it going to be above the pole or below the pole? It's closest to the vertex, it's closest to the pole. So our directrix is going to be here. So our directrix is below the pole, and we have pi over 2 symmetry. So we can already start writing our equation. We know it's going to look like R equals EP over 1 minus E sine theta. Well, let's find our eccentricity. Where's the center? For a hyperbola, just how we always found the center. Halfway between the vertices. So we can find the center. The center is halfway between 1 3 pi over 2 and 9 3 pi over 2. So where is that? F5 3 pi over 2. Halfway between the vertices. So there's my center. What is A? Center to a vertex? How far is it from 5 3 pi over 2 to 1 3 pi over 2, or 5 3 pi over 2 to 9 3 pi over 2? 4. A equals 4. What is C? Center to the focus. 5 3 pi over 2 to 0 0. C equals 5. Well, let's find our eccentricity. E equals C over A. 5 over 4. Is 5 over 4 bigger than 1? Yeah. 5 over 4 bigger than 1? Yes, that's good. Eccentricity of a hyperbola should be bigger than 1. If we came up with an eccentricity that wasn't bigger than 1, we've done something wrong. Well, now we have our eccentricity. We can plug that into our equation. So we get R equals 5/4 over 1 minus, 5/4 P, 5/4 sine theta. I'm going to simplify this a little bit, just so it's easier to work with, get rid of this fraction. I'm going to multiply the top and the bottom by 4. So multiply by 4 over 4. So R equals 5P over 4 minus 5 sine theta. All right, now we need to find P. How can we find P? In your, we don't know where the directrix is, though. We know it's below the pole, but we don't know where it is. Well, in our project, or in the first part of the chapter, if we had a hyperbola that went through a particular point and we needed to find B, what did we do? Plug in a point. Don't we have points that the hyperbola goes through? 1 3 pi over 2 and 9 3 pi over 2. So let's plug in a point. So I'm going to plug in, I'll use 1 3 pi over 2. We have that point that's on the hyperbola. So I'm going to say 1 equals 5p over 4 minus 5 sine 3 pi over 2. Here's the really hard part, remembering what the sine of 3 pi over 2 is. What's the sine of 3 pi over 2? Negative 1. So the denominator becomes 5. 4 plus 5. So I get 1 equals 5p over 9. So p equals 9/5. And I'm going to plug that in here. And my equation is r equals 9 over 4 minus 5 sine theta. And there's my answer. Isn't that nice? We have the vertices, and already we were almost done with the problem. The rest was just a few minor details. And here we found our eccentricity. We could check to make sure that we're doing things correctly. All right, questions? What was that? Why is this so fun? I don't know. It is. That's just the way it is. Yeah. All right, let's look at another example. Let's look at a parabola, and I think we'll all come to love parabolas even more. We want to find the polar equation of the parabola. With the focus at the pole. That's always the case when we're talking about polar coordinates. And the directrix x equals -4. All right, here's why when we see a question about a parabola, we should be really happy. What's the eccentricity? 1. We know that E is 1. It's a parabola, the eccentricity is 1. Well, let's draw a picture. Let's start a little sketch. It says the focus is at the pole, and the directrix is at x equals -4. We know that our parabola is going to look like that. What kind of symmetry does it have? Polar axis. So is it going to have sine or cosine in the equation? Cosine. So we know already this has polar axis symmetry. That our equation is r equals p, because E is 1 over 1. The directrix is to the left of the pole. So this is going to be a plus or minus? Minus cosine theta. All we have to do is find p. How far is it from the directrix to the pole? The directrix to the focus? 4. P equals 4. R equals 4 over 1 minus cosine theta. And we're done. Isn't that nice? So in polar coordinates, really if the problem had just said, find the polar equation of the parabola with directrix at x equals -4, that's all it would have had to tell us, because we know the focus is at the pole, and we're essentially done. All right, questions? Well, very similar to what we did in the first part of the chapter, you'll get some questions that ask you to identify the conic. Just tell us, is it an ellipse, is it a parabola, is it a hyperbola? Let's look at one of those. So we want to identify So I'm going to say the type of conic given by r equals 12 over 3 minus 4 cosine theta. So all it's asking us to do is say, is this an ellipse, is this a hyperbola, is this a parabola? Well, we know that our equation where we can pick out our E and our P, we want it to look like R equals EP over 1 minus E cosine theta. So we need a 1 here. How do we turn that into a 1? Well, let me back up here. Before we did something similar. Here we had this 5/4. What did I do here? I multiplied everything by 4 over 4. So here, what can I do to turn that 3 into a 1? Divide everything by 3. So divide the numerator by 3, divide the denominator by 3. So I'm going to say R equals, divide everything by 3, 4 over 1 minus 4/3 cosine theta. That's E. E is greater than 1, hyperbola. And that's all we have to do. We know that's a hyperbola. We know some other things about it too. What kind of symmetry is it going to have? Polar axis. So it's going to have a horizontal axis. The axis is going to be horizontal. The directrix is going to be to the left of the pole. So we're almost done. If we had to do other stuff with that one, we're almost done. All right, questions? Okay. This is really nice because we did everything that we've done in the first part of the chapter, all in one relatively short lesson. All together, not just in the first part of the chapter, the whole other chapter. We've done polar coordinates, all of that, all together in one lesson. It's interesting because we could do the test could almost just be one question, right? It could be find this, sketch the graph, convert to rectangular coordinates. What else do we need to do? We could just combine everything into just one giant problem. We have part of chapter 10 and part of chapter 11.
Are you going to like match the two together?
Yes. Yes. And part of chapter 10 is three-dimensional vectors. So it's really just stuff we've done with vectors already. We just three-dimensional. And then chapter 11, the part of chapter 11 we do is kind of our little dipping our toes into an idea from calculus.